So this is a restart of the lectures by Harvey Friedman. And yeah, please.
Greetings. So there was a considerable delay because of the upgrading and gross simplification of the subject. The reversal that we were just had started is unchanged. The book title is changed to Invariant Maximality Constructions and Games. And this introduction is not changed because it's not hasn't been written at all. This is the stuff about the second chapter is the stuff about core math with the piecewise linear maps and semi-algebraic maps and invariance notions that are closely related to the invariance notions in invariant maximality in the main subject. This has not really been changed. We won't go over this today. This is the chapter that really introduces invariant maximality and proves all the positive results. This is the positive results section, and that's been revamped. And that's what most of today. This has not been changed, which is the reversal. And as I said, that we'll restart that next week. This has been totally revamped, and this is the finite forms. By finite form here, I mean explicitly pi 0, 1. And this now seems to be in very good shape. It's explicitly pi 0, 1 with absolutely no change. Usually I have some pi 0, 2 form that I wave my hands and say is really pi 0, 1 because of a decision procedure, or I have to add an estimate. Here, the estimates are already in there as a principal feature, and so it's explicitly pi 0, 1. And we'll talk about this at the end of the talk. And then we won't talk at all about this yet. I haven't really spelled that out. Um, but this simplifies this, except that one has to be talking about a game and not a straight statement. So let's uh, do this, and that's what I was saying. Okay, there's only one kind of invariance condition here, and that is this one, which is really partial isomorphism. So if I have a subset of a k-dimensional space, capital X is any set, it's F invariant if and only if F is a partial function from X into X. Double colon means partial function from X to X, where for all X1 through XK in the domain, X1 through XK is an S if and only if F of X1 through F of XK is an S. This is the only notion of invariance. This is the same as isomorphism if F was total. And everybody's familiar with partial ones because you very often build a total one by a series of partial ones. So this is not a totally novel notion. All right. Now, for motivational purposes, and I in the original lectures last year, I didn't really go this well. I can't remember whether I really did this, but I kind of, in baby steps, talk about the construction of these statements. So every widget has a gadget, turns out to be trivial. Every widget has a gadget is kind of an announcement of what the widgets and the gadgets are. Every widget has a maximal gadget is interesting and serious. every invariant widget has a maximal gadget is weaker. We only use one notion of invariance for the front end. This is weaker, but we actually study the maximal gadget being computable, highly computable, exponential time computable, I believe is what we want here. I mean, probably this is subject to some interesting computational complexity issues. And then finally, this is the red meat. This is the main point. Every invariant widget has an F invariant maximal gadget. That's what we really want. Now, of course, the status of four here depends crucially on the choice of function f. And the function f is double colon from our main space into our main space. Oh, I should say already here that we only use one space. So this subject, invariant maximality, has only one space with different exponents, k, only one space with different exponents, k, and only one notion of invariance. And the choice of the function is crucial, is the interesting thing. And f is one dimensional. All right, so let's continue here. So the underlying space is always the rationals, closed interval of rationals from -1 through 1. That's the space. Um, and a square is a set of the form s squared contained in cube minus 1 I'm sorry, this is wrong here. S squared contained in Q minus 2K. Uh, Now, so let E be a subset of Q minus 2K. A maximal square in E is a square contained in E, which is not a proper subset of any square in E. Um, a root in E is an S contained in Q minus 1 to the K, such that S squared is contained in E. And a maximal root is a root which is not a proper subset of any root. More generally, if I have, um, sorry, should be -1. Uh, -1, sorry, uh, -1. Uh, an M root, yeah. You see, I used to use these other spaces. I only use one space now. The interval from -1 to 1 is only what's used here, such that S to the M is contained in E. A maximal M root is an M root which is not a proper subset of any M root. Okay. And note that the roots are the same as the two roots. An Ord square in E is an S squared contained in E, such that every element of S squared is order equivalent to an element of E. And an Ord root is an S contained in everything is always -1 to 1. Such that every element of S squared is order equivalent to an element of E. A maximal Ord square is an Ord square, which is not the proper subset. A maximal Ord root is an Ord root, which is not a proper subset of any Ord root. S is an emulator if and only if S is contained in the k-dimensional space, and every x in S squared is order equivalent to some y in E squared. S is a maximal emulator if and only if it's whatever, as you know, as usual. There's always inclusion maximal always. R is a binary relation on X if and only if R is contained in X squared. S's are free if and only if S is contained in X and for no distinct X, Y, and X is X, R, Y. This is just the notion of free and maximal free. This is standard. And then a graph we're only talking about simple graphs, is an irreflexive symmetric relation. On V, we call V the vertex set, the adjacency relation. Say G is on V and S is a clique in the usual sense, a maximal clique in the usual sense. A graph is order invariant if and only if the adjacent relation is order invariant relation. Okay, and now we start with remember we have these four forms. These four forms, here we are. Every widget has a gadget, every widget has a maximal gadget, every invariant widget has a maximal gadget, and every invariant widget has an F invariant maximal gadget. Um, so we have 9 forms, 9. Used to be 7. Before that, it was 5. Now it's 9 forms. It's there's one for every background and taste. Every subset contains a square. Every subset has a root. Every subset has an ORed square. Every subset has an ORed root. Every subset has an emulator. Every relation has a free set. Every graph has a clique. Every graph has an independent set. Every subset of Q minus 1, 1 to the MK has an M root. I didn't want to go crazy and put variants of this down. Just have one of these, just multi-root. And these names are clear. Now, these are all trivial because you can take the empty set. How about the empty set? That works for each. Now we come to form 2. Every subset has a maximal square, maximal root, maximal ORed square, maximal ORed root, maximal emulator, maximal free set, maximal clique, maximal independent set, maximal M root. Okay. Now there are 2 more forms left. Every invariant widget has a maximal gadget. This is weaker, but we'll be talking about computational complexity here. Every invariant widget has an F invariant gadget. This is where the invariant maximality really lives there. We use only one notion for widgets for the front end. We only use one notion, that's order invariance. So order equivalence, which I'm sure you're familiar with, you've been talking about that a lot. Order equivalence, usual definition, and order invariant set means for all order equivalent X and Y, X is in S if and only if Y is in S. Now we come to form 3. And again, these are the same thing, except we weaken the statements. They're well weaker because we say, and another thing we do, see, since we're making the widgets are supposed to be really nice now, right? Order invariant, order invariant. But here it was just a subset, if you remember. Here, the right thing to do is finite. So here we say finite. This is important. Okay. And of course, ordered variant sets, these ordered variant inputs are themselves finitary objects because of the representation of order invariant sets. Okay, so let's see here. Okay, we can get an exponential time computable maximal square root, ORed square, ORed root, emulator, free set, clique, independent set, M root. I didn't look too much at at the computational complexity side yet. I'll just take a day half a day to think that through. You know, to make maybe I want to make that more definite or precise. Maybe there's some interesting. I think there are probably some interesting computational complexity issues about completeness here, but basically, it's pretty effective to be able to get these things, and you have to be careful what you mean. Base two representations of rationals and stuff like that. But the point is that this is all computational, and in the EFA, exponential function arithmetic. And then finally, we want to come to the main point, which is form four. Now, in form four, these are templates because F is going to be a parameter. We don't want to quantify over F. That's an absolute disaster. We're not quantifying over F. Whereas normally here, we're quantifying over K. See, we're always quantifying over K. There's only one quantified variable all the way through here. And so this depends upon F. So every order invariant subset of Q minus 1 to the 2K contains an F invariant maximal square. That's my lead one. I had to pick one to be first. I picked that one. Okay. Pick that one. And the whole point of invariant maximality is that when you choose F, even very simple F, this becomes a statement that requires large cardinals to prove. And when F is simple, these are all implicitly pi01 via Gödel's via Gödel's completeness theorem. Sorry, Gödel's completeness theorem. These are implicitly pi01. Of course, the problem of getting them explicitly pi01 looks like it is having a very nice solution. That's what took me. That's probably the primary reason why I delayed the lecture series, because I was working very hard to get a good, really good explicitly pi01 form. And I will discuss it or show it to you today. All right. So we have these templates. Now they're really templates because F is varying. We're not quantifying over it. And so we have the 9, what I call the lead templates of invariant maximality. Now, as I said, I've got a version here for just about any taste. And by the way, I should add quickly that there is I did teach a baby form of all this in gifted high school in the Arnold Ross program, which is a famous program for gifted high school students. And the one I picked for them is this one. And the F was very simple. The F was very simple that I used. You'll see later when I talk about some particular Fs, a very simple F was used. And I did stuff for them in 1, 2, and 3 dimensions. No, I think in 1 and 2 dimensions. And I did stuff by hand. Things can be done in there by hand without you doing any machinery. So there was some interest. There's some very interesting things about when do you, as how simple is F and how small is K, so it's no longer possible to do stuff by hand. You have to go in, you'll have to start using some serious machinery. That's an interesting question. All right. Now, to clear the air, I proved that all 9 of these lead templates are equivalent for any parameter F, partial function, Q minus 1, 1, and the Q minus 1. So all of these things are the same. Um, and in fact, and in fact, the first 8 are very strongly equivalent. Namely, they're equivalent K by K. The equivalences preserve the dimension by dimension. The ninth one is not the case. Partly, it's obviously going to be different because there's another variable m in there. Okay, but nevertheless, the full statements are all equivalent, including the ninth one. The first 8 are very equivalent. All right, so and then dimension k equals 1 is completely handled in RCA naught. Dimension, as you'd expect, dimension k equals 1 is really nothing exciting. P is affected by F if and only if there exists Q not equal to P, such that F of P is equal to Q or F of Q equals P. Um, okay, that's what it means to be affected. So these 8 statements hold for k equals 1 if and only if there's some number not affected by F. That's a very weak condition on F. And and then for it's hard, it's a little bit more involved for the multi-root thing. Multi-root thing holds for k equals 1 and m greater or equal to 1. Um, if and only if and only if F has the property that the forward image and inverse image of some S um, sorry about this. The forward image and inverse image of S under F is contained in S for some less than M element S. Yeah, so you have a necessary and sufficient condition when this holds for k equals 1. Okay. Anyways, that's not really important for this, that important, but it's nice. Once k equals 2, this is very serious stuff. It seems to be second order arithmetic is needed. I mean, I never reversed that. The only reversal I actually worked out is the one we're going to do, which is all the way up to SRP. And and you have to have a decent F to be independent. This is coming up soon here. All right. Now, here's something new. I I have all these 9 things. I wanted them to be very specific and uh, be something for everybody. But then the question is, can I consolidate this into one without having all these different notions that are for all these different minds? So I looked into this, and this leads to some interesting things. Um, so the first thing is a pretty straightforward equivalence. An order invariant constraint on the subsets of Q minus 1K is a condition of the form for every x1 through xn in S phi, where phi is a propositional combination of statements that the rth coordinate of xi is less than the s coordinate of vj. Um, yeah, you see, these x's are tuples. These x's are tuples, so I want to pick out the coordinates. Where I and j are between 1 and n, and r and s are between 1 and k. Okay. So basically, intuitively, this says an OI constraint is a statement of the form if you take any n elements of S, there's some order theoretic relation that must hold among them. That's basically what I'm saying, except that it's stated logically with propositional combination. Okay. Now, this turns out to actually be okay. So now we have the following statement. I write it this way: max OI constraint F. So every OI constraint on the S have an F invariant maximal instance. We know it has an instance, namely the empty set is an instance, right? If S is empty, this is vacuously true. So we ask for an F invariant maximal instance. Now that statement isn't involving nine different things for nine different minds, right? So we have a nice statement here. Um, but this statement is equivalent to all these other statements. So it's a consolidation. And it's pretty easy to prove this because this statement is extremely close to the multi-root version. And if you remember, I said all nine of them are equivalent. So that's why this theorem is true. Okay, now this led me to go off the deep end a bit and consider the idea of stronger conditions that we can put on S. And this needs to be written up um, carefully, but I know in principle this is right, at least. I'll show you what I mean by that in a second. Um, so the field of S is the set of all coordinates of elements of S. And the universal properties of the S are the form, this structure goes from -1 to the sup of the field. See, I want to keep this somewhat related to S. This structure, comma less comma S, satisfies phi, where phi is a universal sentence in the sense of logic. See, this is stronger. Um, I mean, there are more universal properties than there are constraints, right? Constraints are a special case. And the reason this is actually new is because now we can mention S negatively. We can talk about what's not an S, see, as long as it's bounded by S. Okay, and now I claim that every universal property has an F invariant maximal instance. I mean, I'm not claiming this. This is a template, and I'm saying that that this template is the same as the other as everything else. Now, we can even go further, as this is as far as I can take this, and this gets tricky. I'm not 100% sure about this, but let me tell you what I'm pretty sure of, even if this isn't quite right. Okay, an A star E star property is the same thing, except that the sentence is AE. A star, E star, the sentence phi. And we still want to bound this thing by the I was talking about the soup of the field. You remember the soup of the field here. All right. Um, so every A star, E star property of the S has an F invariant instance. It's a little bit of a stretch. I think it's correct that this is also equivalent to everything else. But even if it isn't, I know how to use this in invariant maximality. So for the Fs that I care about, it's equivalent to these other formulations. For the F I care about, the only issue is whether I can make this so general that it's the same for all Fs. I'm very likely I can do that, but if not, I can make it. I'm much more certain that I can that for the Fs I care about, this is equivalent. Okay. I mean, for many Fs, there are Fs for which everything's false. You can't. Uh, by the way, for one thing, if any of these statements hold for F, F has to be strictly increasing. I should just add that in passing. All right, now it's useful to have a notion of usable. So F is usable if and only if you can use it in all or some of the lead templates. I.e., F is usable if and only if OI max root of F. I just picked one of them, one of my favorite ones. I picked that my favorite one actually. OI max root. Okay. Now, I've been able to characterize the finite usable F. So we now have a subject. The subject is what Fs are usable. And I know what the finite usable ones are, and I call this result fin use. A finite F is usable if and only if F is strictly increasing. Remember, these are one-dimensional objects, F. Strictly increasing, and both of these things fail. -1 less than F of -1 and F inverse 1 less than 1. This makes sense because F is strictly increasing here. Of course, F inverse of 1 might be undefined, in which case this is automatically false. Okay. Or -1 is less than F inverse of -1 and F of 1 is less than 1. Both fail. In other words, you have to be, in order to be usable in the finite case, be usable, you're okay if the endpoints behave themselves. But otherwise, there's two kinds of obstructions to being usable, two kinds of obstructions, and those are the two. Now, the forward direction of thin use is proved in EFA. In other words, usability implies you better not have these obstructions. That's proved in EFA, but the converse needs conPA, as far as I know. Oh, I didn't try to reverse this. I think I can, but I haven't gotten into that. So when you prove the other direction, you will be using some machinery. And this is related to using the right endpoint, which becomes a limit point, and you become a PA person of some sort when you prove this thing. All right, or an ACA naught person, really, that kind of thing. But it's all finite. It's all implicitly pi 0, 1. So basically, this has to be the cause of what's happening, really. All right, now the set theory arises when you talk about when you go to the realm of the infinite maps, the infinite maps. And this arises in extremely simple infinite maps. Um, Essentially, the simplest infinite map, I should say this, essentially the simplest infinite map, infinite, have the following, are shaped like the ones below. I should say it that way. Are shaped like the ones below. Okay. And here I'm borrowing notation that's actually very similar to the notation, not exactly, but very similar to the notation in that chapter 2, which is about the core math, the piecewise linear and piecewise algebraic functions. This is not quite the same notation, but close. Okay, so there's some unification here of notation. All right, so less than zero, semicolon, 0 over n to n over n is a map from q minus 1, 1 to q minus 1, 1. By the way, I do know enough arithmetic to know that this is 0 and that's 1. But I want to leave it this way to show the pattern, that it's a nice arithmetic progression. By the way, everything's order theoretic, so this is just convenience because it doesn't make any difference what these numbers are. It's only the shape of the numbers. But it's very important that this is the right endpoint, that this is not the left endpoint or the right endpoint. Okay. All right. This is the map that has domain from -1, 0 union these numbers. So it's a partial map. And it's the identity below 0 and maps each I over n to I plus 1 over n. Now, we actually prove uh, that this is usable. We actually prove that this is usable, this map, uh, for dimension k equals 2, no matter what n is, for dimension k equals 2 in third order arithmetic. And, there's a likely reversal. You can't do it in second. Again, I haven't, the only reversal I've really gotten into is the big one we're going to do, which is for SRP. And then if you make the n equals 2, so uh, we have this 0, a half, 1. Um, that this is provable in Z3. Now, I'm a little bit worried about whether I have to look. I'm a little bit worried. Let me go. Let me look back at that. I think, something, I think that I meant this because that's the one that this is the one that I talked to the high school kids. I discussed with the high school kids in a small dimension. This is arbitrary dimension k. Yeah, I think that I'm pretty sure that I said this wrong. So I think this is what I meant. Yeah, let me clean that up. I think that's right. Yeah, I may have screwed this up. Yeah. All right. So now we actually prove this for all n, and k is the dimension. I always use k for the dimension, and n is another parameter here. Um, so for all dimensions k and for all n, this is proved in SRP plus. That's a large cardinal hypothesis that for every R, there's an SRP R cardinal. Okay. And and then I fix that up so you can just use WKL naught plus con SRP. Okay. All right. There may be something a little bit funny about this, but I think this is okay. I think this is what I meant. All right. The point is that I only use the amount of subtle cardinals in the SRP hierarchy, so to speak. It depends on that I use depends on the parameters K and N. Yeah. I mean, yeah, okay. Let me think that there may be, yeah, okay, maybe off by one or something, but I think it's basically, I have to get clear about this. All right. Now, in the big reversal um, is this. I look at OI max root. Actually, it isn't this one. Actually, I'll say actually, the equivalent one, the one that I actually use is click. This is what's reversed. Yeah. Where the dimension K is the same as the dimension K is the same as the K used for the fractions. Okay. That's and it turns out it's very nice that I originally did the reversal on Q minus 1, when I was actually making the subject in bigger intervals and just saying it's equivalent. Whereas now I decided to make everything in Q minus 1, which is, much nicer aesthetically, that everything is Q minus 1. All right. Now we're going to go more generally beyond this. A basic almost identity is a function F union G, where F is finite and G is the identity on a finite union of intervals with rational endpoints. And I'm now claiming a very strong result, uh, although this doesn't come close. Okay, the big problem is which basic almost identities are usable? Which basic almost identities are usable? And I'm very far from being able to solve that problem completely. Now, among the basic almost identities are, of course, these, because this is the identity on an interval, this interval, but less than zero numbers, negative. And then there's this finite part up here. So, um, but the general case, there can be some finite stuff here, and then some interval here, and then some more finite stuff here, and then an interval here, and so forth. Um, of course, as I said, strictly increasing is the only thing of any interest, because in order to be usable, you have to be strictly increasing. This is a basic thing. Uh, and then it becomes quite dicey exactly what happens when especially when things are quite thick. In other words, there's not a lot of open spaces. Open spaces make things in some cases easier. All right. So I'm claiming this. If F is a strictly increasing basic almost identity with F of minus 1 equals minus 1, then it's usable. Strictly increasing basic almost identity with F of minus 1 equals minus 1, then it's usable. I think this is true even if it's not basic. See, there's a notion of almost identity in which the identity function doesn't have to be on a finite union of intervals with rational endpoints. It can be on any set. And I think that because it's strictly increasing, you can extend this map to a basic one. And so I think this is true without the word basic. Uh, but it's the basic ones that I care most about because they're the ones that are very explicit. And of course, if I prove this in WKL naught plus con SRP, and it is implicitly pi 0, 1, I'm obviously going to be able to reverse it because a special case of this is the case that I reverse over here in chapter 4. So it would be equivalent. All right. I'm going to finish today by telling you about where I am with the finite form, and which is actually a long story. It was a long, tortuous battle. I was looking to shake the entire universe, but I wasn't quite able to do that. Uh, uh, okay, so that's in chapter 5. I used the upper shift, and that adds 1 to all non-negative coordinates. So the upper shift of a rational is the rational itself if it's negative, and it's the rational plus 1 if it's non-negative. And the upper shift of a tuple, the upper shift of a tuple is just the tuple of the upper shifts. And then I also use the height, which is a standard notion. The height of a rational number is the greatest magnitude of the denominator and the numerator when you put it in lowest common terms, lowest common terms. And when you have a tuple of rationals, the height of a tuple is the max of the heights of the coordinates, is the max of the heights of the coordinates. And the idea being here, of course, that this is a very convenient way of talking about uh, uh, the complexity of a rational tuple. There's only finitely many rational tuples of a given dimension and the most height. Yeah. There are only finitely many rationals of height at most n, only finitely many rational vectors of height at most n and dimension k. And it's a function of k and n. Okay. All right. Now this statement is OI height USH. In every ordered invariant graph, so here I use graphs. In every ordered invariant graph, now in this subject, which I call finite invariant constructions, in this subject, I do prefer going to the intervals q minus nn. See, if I stick at minus 1, 1, the right endpoint would have the smallest height. If I stick with this, the height of the right endpoint is quite significant. The height of the right endpoint is n. All right. Because I'm using heights, I really do care about whether it's now minus 1, 1 or minus nn. Okay, so in every order invariant graph on q minus n, n to the k, any vertices, oh, I forgot to tell you what touch means. Touching in a graph, vertices, VW touch in a graph if and only if they are either equal or adjacent. Okay, there we are. Okay, in every ordered invariant graph on q minus n to the k, any vertices v1 through vr, upper shift vr. Now, the upper shift of a vertex might not be a vertex, but so I'm demanding that the upper shift of vr be a vertex because you might overspill you might go over little n. Okay, so any vertices V1 through VR, upper shift VR, respectively touch independent vertices. Independence uh, means the vertices are either equal or not adjacent. Okay, it's the usual notion of independence. Uh, respectively touch independent vertices W1 through WR, upper shift WR, where each height of WI is less than or equal to a simple, it's probably a double exponential function of K and the height of VI. Now, it's very important. This is some function I'm too lazy to compute right now. I will shortly when I write this up completely. Okay, so it's very important that this expression here not mention R, so I can go to the compact limit in the reversal. See, this is going to reverse to something hot. This is going to reverse to you know uh, one of my statements. All right. So as a bonus, you actually, with more care, can make sure that n is not even in this here. That this is only a function of k. This is only a function of k and the height of vi. There's uh, no mention of n as well. All right, now this actually leads to a lot of interesting questions that I don't know the answer to, and a lot of possibilities that I won't really go into right now. But anyways, I have some confidence that I can reverse this, so that this is equivalent to con SRP over PRA. And obviously, this is explicitly pi 0, 1. There's no issue. And print recursive arithmetic. Actually, it's probably true that you could use the FA, but that's going to take, I think that takes some extra work to actually do that because I'm passing through the reversal. If you remember, the reversal used RCA naught. I mean, it was better than using a WKL naught, but it could use RCA naught, and RCA naught is conservative over PRA. So that's how the PRA comes in, although probably one could do better. Well, that's the end of my talk, Andreas. And uh, let
Yeah.
me field some questions.
Hmm.
Yeah. I should say, for those of you who came in late, uh, I should tell you that what happened was I spent all this time coming up with this and also rethinking everything, streamlining everything on to go to nicely to go to one space and one notion of invariance. In other words, the only space is q minus 1, 1, and the only notion of invariance, only one notion of invariance, and that's this one here, which is just partial isomorphism, which is familiar to everybody. Even the mathematicians is familiar to them because when they build a total isomorphism, they're often building it as approximating it by finite ones.
Okay, fine. I will now stop the